Record to the cloud. Okay, everyone. Welcome back. I haven't talked to you all about the exam grades. The exam grades, like I said in my announcement yesterday, they were about an 82, I think was the average. I think the highest grade was I think there was a 94. Um, and there were lots of grades that were I mean, as I was kind of scanning through the grades, it was seemed like 81 to 86 was the most consistent grade. So that range. And I felt like it was a good even test. I felt like it was fair. If I remember correctly, you should now have access to your results. Is there anyone who can kind of confirm that? I've got a couple people on video. Has anyone looked back to see that they can see their results, like their answers and everything like that? Um, you don't have to do that now, but if you wouldn't mind, I believe that it's set to make them available. But if you look and you cannot see it, let me know and I'll go back and look at my settings a little bit later today. And that's one of the things that I want you to be able to do is to look back at your exam so that you can see, okay, well, here's what I got right, here's what I got wrong. Okay, Christian, thanks for the response. I'll take a look at those and make sure that you guys can see those a little bit later today, so you can see the correct answers as well as the incorrect answers. Um, what we're going to be doing today is amino acids, and we're going to be talking about our amino acid structures. We are going to kind of narrow this down a little bit, and I've got my doodle pad here. We're not talking about like amino acids. We're specifically going to be talking about proteinogenic protein. How about I spell it right? Ogenic. Um, and I bring that up just because when you hear the term amino acid, what I want you to do is not think about this as like, oh, this is a unique molecule that makes life happen, yay or nay. But instead, I want you to think about this term and break it down a little bit. If you go back to Gen Chem 1, that was the first time you ever heard what an acid was, right? And then it probably took until, maybe in Gen Chem 2, your instructor mentioned an amine, just as like a base or an acid, something that could gain or lose an proton. But then it was inorganic where you really started talking about your nomenclature, and you said this was, well, an amine as a functional group. But whenever you see this term, I want you to think about amino acid as just being something that has an acidic group and an amino group. Um, I think it's helpful to do that because when you think about an amino acid, they're actually really much more abundant, much more common than you might think. With that in mind, if anyone is drinking an energy drink, and I think the biggest, not necessarily culprits, but the most common examples of this are taurine. If you drink Monster energy drinks, on the rim of the label or on the rim of the can, you might see something like taurine. Similarly, I think that Monster or Bang has carnitine. And these are both amino acids because they have an acidic group and an amino group. But these are not the amino acids that we're going to be talking about. We're going to be focusing primarily on proteinogenic amino acids. So these are the amino acids that make up proteins. These are your so-called building blocks of proteins or building blocks of life. So we're going to go through this and we're going to talk about some of the high points of these molecules, and what I think is going to be most helpful for you as you understand these structures. So our learning objectives for today, amino acid classification, nomenclature, and structure, ionization of amino acids, PI calculation of amino acids, as well as peptide and ionization of peptides. So we'll start with individual proteinogenic amino acids, and we'll go through a process of, okay, how does this molecule change based on pH? And then we'll say, okay, we can take one of these individual amino acids and add another one to it, and we'll make a peptide, a polymer of amino acids. Now, how does the resulting molecule change based on the environmental pH? So it's almost like we're learning one skill and then we're going to apply that same skill to a slightly different molecule. Now, with that said, I want you to think back to probably, I think that in Gen Chem 2, you probably learned about acetic acid as a great example of an ionizable molecule. Acetic acid has a formula of CH3COOH. And if you look at acetic acid, one of the things that stands out that really becomes a big thing in organic is this molecule right here, or this portion of our molecule right here. This is our functional group, and this is a carboxylic acid. I know that I have a habit of just writing a carboxylic acid as COOH, to the point that whenever I hear the phrase carboxylic acid, I'm already writing COOH. I almost say like co instead of carboxylic acid. I try to say the functional group. Now, that molecule right there, well, it changes based on pH. The way that I've drawn this molecule right here, well, this is the form of the molecule when my pH, or when it is in a solution with a pH of below 4.8. If my pH is above 4.8, acetic acid is not really going to look like this. And it's actually not going to be acetic acid. Instead, it's going to be acetate, an acetate ion, because at a pH of above 4.8, we're going to lose this right here. Okay, now on the opposite end of this, ammonium. Ammonium is a molecule, NH4+. Now, I remember it's really kind of tricky, or for me personally, it was tricky because I would always get ammonia and ammonium mixed up. I would hear ammonium and I'd be like, oh, well, that's NH 3 or 4. And I just kind of bank on, okay, well, hopefully if that surfaces on an exam, I'll just flip a coin and get it right. Well, ammonium is NH4. NH3 is not ammonium. NH3 is ammonia. Ammonium, if you go back to Gen Chem 1, that was one of your polyatomic ions that your instructor probably asked you to know. And if they didn't ask you to know that explicitly, they certainly introduced it to you and they said, this is almost the only polyatomic cation, the only positively charged polyatomic ion. So these two molecules, acetic acid and ammonium, if you understand what those look like in different environments, in different pH environments, you're going to be in good shape for analyzing amino acids, because at their heart, you really just care about how acetic acid and ammonium are ionized. Now, acetic acid is going to look like this, our two different conditions. And I know that my Zoom display is a little bit different from y'all's, but can everyone see that entire, or both of those entire molecules? Wonderful, because I've got the array of pictures and everything like that. Cannot see them. Yes, okay, cool, great. So on the left-hand side is our acetic acid, and on the right-hand side is acetate. Those are our two forms of our molecule. Acetic acid has a pKa of approximately 4.8. In some sources, you might see it as 4.7. I'm not going to ask you to know those pKa values, but I think that there's a couple that are just like, it's going to save you some time if you remember what they are. Now, a titration curve for acetic acid is going to be kind of boring. It's going to look like that. It's going to start out low, and then at some midpoint, which at approximately 4.8, you're going to have this right here, which corresponds to my pKa. Now, before I proceed from here, I want you to look at my x-axis. My x-axis ranges from 0 to 0.5, 1.0. This is the deprotonation of a molecule that has a single proton. So it has one ionizable group. At some point, this molecule is going to be 100% looking like this. And that's going to be somewhere around here, where my pH is at this point and higher. Now, alternatively, at an extremely low pH, for all intents and purposes, if you're at a pH of, pH equals 0.5, which typically when we talk about pH, we give a range from 1 to 14, but it can be higher and it can be lower than that under kind of theoretical circumstances. At a pH of 0.5, 100% of my molecule is going to look like this right here. Now, I want you to kind of visualize this and then think about points along the way. If we're right here, whenever you have the time, would you be able to upload this PDF? Doesn't allow it. I believe today's is up as a PDF. Is it not? It's not as a PDF. Okay, let me fix that right now. Oh, yep, sorry about that. Okay. Sorry, everyone. I'm going to pause my recording so we don't have this in the midst of the meeting. So just okay, so here's our kind of opposite ends of the spectrum. If we are at this point right here, we have an environment where our pH is, let's call it 4.6. It doesn't really matter specifically. Let's call it 4.6. That pH is lower than our pKa, so this form of my molecule, the acetic acid, is going to be more abundant. Is there any acetate in the solution at a pH of 4.6? There absolutely is, but it's a lower concentration. So at a pH equals 4.6, we could go ahead and say that it's 60% AA for acetic acid, and let's call it 40% acetate. Now, if we move to this location, which I'm going to label Y just to contrast, well, then it's going to be approximately 40% AA and 60% acetate. Understanding that and understanding the concentrations, the give and take, that's going to be extremely important for thinking about things in a solution. So we've got acetic acid and acetate. They balance one another off. Now, with that said, if we put acetic acid and let's say we make a solution and we just add a bunch of hydrochloric acid, the pH is going to be down low. It's going to be low, 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 low. And we keep adding more hydrochloric acid. If anything, the pH is going to continue to drop or it's going to stay low. Now, my question for y'all is, in this environment where we have acetic acid, we're adding more and more HCl, trying to make it as acidic as possible. Is acetic acid ever going to have a +1 charge? And I saw at least one person do this. And that is the very clever Zoom response of no, where it's like, I'm going to move my head so slowly that you might not be able to pick up on it because you're watching at least 3 people. And the answer is no, it's not. You're absolutely right. For those of y'all who, with your cameras on or off, did this, you're right. Acetic acid is effectively never going to have a +1 charge. Whenever it's as protonated as it can possibly be, it's going to be neutral. And that's a little bit counterintuitive because I know whenever I think of protonation, gaining a proton, I think of gaining a positive charge. So I think, oh, well, I've gained a positive charge. That means I'm positive. Well, yeah, but you're only positive if your starting place was neutral. Well, our starting place or our comparison, our form of this molecule that can gain a proton is acetate, a -1 charge. So when a -1 molecule gains a +1, it becomes neutral. Now, let's think about the opposite end of the spectrum. When acetate goes to an extremely high pH, is that ever going to have a -2 charge? No, it's not. This molecule, acetic acid, is going to, and I like to use this word, it's going to oscillate. It's going to bounce back and forth between either a -1 or a 0 charge. Acetic acid is not going to be +1. It's not going to be -2. As acidic as it can possibly be, it's going to be neutral. And that phrase right there sounds counterintuitive, but its overall charge is going to be neutral. It's going to be 0. If you could understand that, that's going to be also very helpful. So thinking about the capabilities and the spectrum or the range that a molecule can take on is going to be very helpful for visualizing amino acids. So now when we look at ammonium, let's think about the same thing. Ammonium is going to have a titration curve like this. Ammonium is a monoprotic acid or a monoprotic base, depending on your kind of vantage point or your perspective. At a neutral pH, at a pH of 7, which form of these is going to be more abundant? Ammonium or ammonia? Well, at a pH of 7.4, that's right about here. This form of the molecule, ammonium, is more abundant on the left-hand side of my titration curve. On the right-hand side of my titration curve, this is going to be more abundant. So if at the pH of 7.4, ammonium is going to be +1. At a pH of 1, spoiler, this might be a little bit of a downer, but ammonium is still only going to be +1. It's not going to be +2. Now, let's go ahead and adjust this by adding more and more hydroxide. So we're increasing our hydroxide ion concentration. And then we get here. At this point in time, ammonia is going to be more concentrated than ammonium. As we continue to raise our pH, we're never going to have an ammonia that is -1. This molecule is going to oscillate between +1 and 0. +1 and 0, 0 and +1. That's basically all there is to it. It's never going to be +2. It's never going to be -1. That's our range. So those two functional groups are essential for understanding and visualizing an amino acid backbone. These amino acid backbones are kind of based on, or I always love to compare them to, ammonium, because what is ammonium but a nitrogen with 1, 2, 3, 4 bonds to it? A nitrogen with 4 bonds has a +1 charge. It has a pKa of approximately 9.3. Then this is almost acetic acid. The difference is, well, rather than that carbon, this carbon right here having a total of 4 hydrogens coming off of it, it's got a nitrogen, a hydrogen, and a R group. We've got a carboxylic acid, that carboxylic acid, COOH. That's our ionizable group. And this backbone for this overall molecule is going to have, well, 1, 2 ionizable groups. So what that means is every single proteinogenic amino acid that we talk about is at very least a diprotic acid. So it's got 1 and 2 ionizable groups. There are some amino acids that will give us a third R group or a third ionizable group. So that would be our third, but not all amino acids. So before we get to that, we can look at the amino acid backbone for most amino acids. And what I love to do, what I prefer to do, let me say, is I prefer to draw the amino acid backbone in an aqueous environment where the pH is as low as it can possibly be. That's helpful for me because then I have this kind of definitive, well, here's my extreme. Rather than drawing it at a neutral pH, I like to draw it at a pH of approximately 1. And I like to just say, oh, this is at a pH of 1 for all intents and purposes. So what that means is that if I have a divalent or a diprotic amino acid where groups 1 and 2 are both protonated, what is my extreme charge of this? +1. Now, what I will do is this would be, you could look at this as my cationic form. Then I'm going to add a strong base like sodium hydroxide to it, so I'm going to begin deprotonating it. One group is going to be losing that proton. The first group to lose that proton is the group which has the lower pKa. And between my groups that have my pKa's, well, my carboxylic acid is going to have a lower pKa. I gave you this slide right here where it was 4.8, but usually as the amino acid backbone turns, it's going to be approximately 2.5 or something like that. I will give you those specific values for questions where you need this information. But like I said, it saves you a little bit of time to say, okay, well, the group on the right, my carboxylic acid, I remember carboxylic acid has a pKa of approximately 2.4 or something like that. So I'll deprotonate that group. When that group is deprotonated, I have what is known as my Zwitter ionic form of my amino acid. Now, this Zwitter ion form or this Zwitter ionic form has both a positively charged group and a negatively charged group. Now, with their powers combined, what is their overall charge going to be? 0. A +1 and a -1 on the same molecule will cancel one another out and give me my form of my molecule with an overall charge of 0. My last group is going to be the result or deprotonated from more base being added. So I'll lose this last proton, and now I have what I can refer to as my anion form. So I have a cation form and an anion form. Now, so what this shows you is just the backbone. Like I said, these R groups, many times they are ionizable, but every single amino acid is at very least a diprotic amino acid. There are some that are triprotic, but every one is at least diprotic. And so if I were to say, hey, there's a diprotic amino acid, I want you to think, okay, what are my extremes? That diprotic amino acid can be +1, 0, or -1. Those are the three possible charges that that amino acid can have. So diprotic has a range from +1 to 0 to -1. So if I were to pose a question to y'all like a diprotic amino acid that has a -2 charge, you'd know that something's off or that question is flawed because the diprotic amino acids, diprotic proteinogenic amino acids cannot be -2. They can be +1, 0, or -1. This is ranging from a pH of 0.0 all the way up to 14.0. No matter what the pH is, this molecule, a diprotic amino acid, is going to be +1, 0, or -1. Now, a diprotic amino acid is going to have a titration curve that looks a little bit like this. I always like to draw titration curves because it gives me the opportunity to kind of visualize where experimentally I see the different forms of my molecule. So what I like to do is I'll take at 0.5, or sorry, I'll draw my three different forms of my molecule. And again, this is kind of my base model diprotic amino acid. I'm going to draw a dashed line from 0.5 going up. Then I'm going to draw a dashed line from 1.5 going up. I have three different forms. And what I can do is I can label these A, B. You know what? Actually, I'm not going to go A, B, and C. Instead, I'm going to make it a little bit more relevant to the terminology that we're using. The one in the middle, I'm going to label as my Z, or my Zwitter ion. The one on the left, I'm going to label as my C, or my cation. And then on the right, my A, or my anion form. I drew these, or I displayed these left to right intentionally to align with my titration curve. C is going to be the most common from 0 to 0.5. Z is going to be the most common form of my molecule from 0.5 all the way up to 1.5. And then A is going to be my most common from 1.5 basically and above. And I'll give myself arrows going in both directions here. So this is important because the way that I want you to kind of think about this and visualize this is I want you to think about this in terms of the predominant, the most common form. So if I were to say, hey, you've got a diprotic amino acid and your pH equals, let's go with 11.2. What I want you to be able to do is look on the y-axis and say, okay, 11.2 is approximately here. Now, which is my most common form? And I'm going to kind of draw all over this, but I'm going to draw a straight line right across, and I want to meet up with my titration curve. So the most common form of my molecule at a pH of 11.2 is A. Now, if I were to change that question and say at a pH of, let's go with 6.1. Okay, 6.1 is right here. Ooh, my most common form is Z. Now, where it gets a little bit tricky is let's take this 6.1 point. And we're going to come back and do this sort of calculation in a little while in more detail. And just to, like, this is the sort of thing that I have no qualms with, like, belaboring it. There's a couple pieces of terminology that you should be aware of and thoughtful of. You have your predominant form, and then a similar, like a fishtail or dovetail type of question that can come from that is, well, what is the second most common? Or what are all of the forms of the molecule? Or what are the most common forms of this molecule at this pH? So at a pH of 6.1, as you can see, I'm going to draw my line and, would everyone agree that this line, the slope is still increasing? It's not quite at 1. It's not vertical at this point right here. Would everyone agree with that? It's nearly vertical, but it's not straight up and down. Oh man, that was a bad straight up and down line. But would everyone agree with me that that is not a vertical point in this line? It's definitely getting more and more steep, but it's not there. So that's an important point to think of. When we are at pH of 6.1, we actually have a combination of two different forms of our molecule, and they are C and Z. If you were to look at 6.1, I mean, I would feel comfortable saying it's 99.9% Z and 0.1% C. Now, if we call, so then this is one of the tricky parts, or this was always tricky to me about general chemistry too, was you have equilibrium. You have this situation where, well, it's, the reaction hasn't stopped. Instead, you're at equilibrium. And so it's almost like, well, there's no definitive point. And you can't say like, oh, it's 100% this form of the molecule, because as soon as you say that, then it's like, well, this is in equilibrium. So there's, 0.00001% of the molecule that looks like this. Now, to bring that up and to kind of emphasize something, there is a place along this curve where we can say 100% of our molecule, 100% is Z. And this is tough, but what I want to do is I want you to think about a couple of different locations. This first X, that is my first pKa. And that is going to be the place where I've got 50% of my molecule that looks like this, and 50% that looks like this. Okay, so that's where that X is. Is everyone good with that? Okay, now I'm going to draw a Y. That's supposed to be a Y. That location is where 50% of my molecule looks like the Z, the Zwitter ion, and 50% of it looks like my anion. Would everyone agree with those points? Okay, now we saw right here approximately another X where it was like 99.9% C and 0.1%, or sorry, that's Z, and 0.1% C. If we compare that to this location right here, my question for you, has the concentration of Z, has it gone up? Another way of phrasing it is 99.9 a larger number than 50? It is. So this location, my first pKa, it was 50% of my molecule was Z. And then as I continued raising my pH, 99.9% of my molecule became Z. So what I saw was my concentration of Z went up. And as a result of that, my concentration of C went down. So would everyone agree with me that as I continue to raise my pH, my concentration of Z is going to go up from 99.9%? And would you agree with me that it's potentially going to go from 99.9 to 99.99 to maybe even, let's just call it 100? Does everyone follow me there? Okay. Now, there is a specific location on a titration curve where you can identify that specific location. And the way that you calculate it, I think yeah, there was a chat. Okay, good. What we can do is we can take our two pKa values. This is approximately 4.8. This is 9.3. There's one specific location right there where 100% of my molecule is Z. That is where my curve is as vertical as it can possibly be. If you were doing a titration in Gen Chem 2, you would refer to this as your endpoint. This is a location between my two pKa's. This right here can be calculated by taking my two pKa's, 9.3 plus 4.8 and dividing them by 2. And let's call that 14.1, so 7.05. If my pH equals 7.05, 100% of my molecule is Z. Does that make sense? Okay, so if I have a solution where my pH is exactly 7.05, what percentage of my molecule is my cation? If 100% is the Zwitter ion, 0 is the cation. If 100% is my Zwitter ion, what percentage is my anion? Also 0. Does everyone follow that? Okay. Now, being able to do that is important and will be important for something known as an isoelectric point, or a PI, which we'll get to a little bit later today. Now, I've spent a good bit of time on this because it's important, because it's valuable, and not only will it be valuable on the exams that I give you, but it will be valuable anytime that you're talking about, purifying a protein or purifying an amino acid, understanding the form of the molecule that you're looking at. Now, with that in mind, we're going to look at our proteinogenic amino acids. These are your 20 proteinogenic amino acids. We've got a total of 4 rows of 5. Alanine, isoleucine, methionine, lysine, glutamine, aspartic acid, asparagine, valine, leucine, proline, tryptophan, glycine, tyrosine, threonine, glutamic acid, serine, cysteine, histidine, phenylalanine, arginine. I want you to be able to identify all 20 of these structures. This is something that, when you look at it like this, some of your facial responses and reactions are what I've grown to be completely immune to. And no, I'm being facetious there. This is like the 72-ounce steak. You look at it and you're like, oh goodness, that's a lot. It's a lot to process. If you're preparing for the exam or for like the MCAT or something like this, you've probably seen these before. What I recommend doing is not trying to consume them all at once, and instead break them down. Now you can kind of look at these, and there's a couple of things that should stand out to you. By a show of fingers or adding to the chat, how many molecules have yellow atoms in them? 2. Okay. Those are 2 outliers, methionine and cysteine. Done. If you were to get a question on either my exam or an MCAT or anything else, any biochemistry class, like if you decided, after today, you're like, I'm not going to take this class, I can go take it at UT, I'm going to take it at UTSA or something like that. I don't really understand why you do that. I mean, personally, respect, that's your decision. But I think that, or my point is that you would be able to immediately answer the question, which amino acids include sulfur? Our yellow atoms are sulfur. Now, those are 2 things that stand out. So 18 of your 22 or of your 20 proteinogenic amino acids that remain don't have sulfur. Now, you can look at these a little bit more closely, and you can draw some other comparisons. For instance, if we look at this right here. Why is my pen not being a pen? Oh, there we go. It's just a little delayed. Does anyone else see a positive group that I circled? A nitrogen with a total of 4 bonds going to it. Now, anytime you see a nitrogen with 4 bonds, I want you to think back to, oh, well, what was our nitrogen with 4 hydrogens? Ammonium. Ammonium is our positively charged polyatomic ion. Okay, nitrogen with a positive charge is going to, or sorry, an amino acid R group with a nitrogen that has 4 bonds to it is going to have a positive charge. Now, if you were to look at, so I'll save us a little bit of the remainder of that speech, but the way that I've displayed these molecules is different from if you go to Wikipedia, if you get a biochemistry textbook, because if you get a biochemistry textbook like this one right here, Leninger's Principles of Biochemistry. This is the 7th edition. And if you flip through it, chapter number 3 has amino acid structures. And if you look at it's not really going to be in focus, but one of the things that I want you to notice, or if you pull up a biochemistry textbook or any other resource, if you do Google image search for amino acid structures, one of the biggest differences between the way that I display them here in this figure and any other textbook is the way that I've drawn them is at a pH of 1. Every group that can be protonated is protonated. Now, that's something that always sort of stands out to people as like, well, that's okay, interesting, cool, got it. If you look at the backbone of every single one of these amino acids, it's got that NH3 or a nitrogen to carbon bond, and then 3 hydrogens coming off that nitrogen and a positive charge. If you look at your carboxylic acid, you've got a carbon-carbon bond and then a COOH, no charge whatsoever. So the backbone is drawn at a pH of 1. Every single one of these R groups is as protonated as they can possibly be. Now, if we look at this amino acid right here, asparagine, the R group for asparagine looks like this. The R group for asparagine, my question for you is, do you see a positive charge indicated with a little plus sign? No. Do you see a nitrogen? Yeah. What does that nitrogen have? That nitrogen has a total of 3 bonded atoms and a lone pair of electrons. A nitrogen with 3 bonded atoms and a lone pair of electrons, what's the overall charge on it? Or what's the formal charge of it? 0. If it has anything, it has a partial charge, but it's not going to have a formal charge of +1 or 0 or -1 or anything like that. So the way that I've drawn this is asparagine is not a positively charged amino acid because it's not. Okay, now this detail right here is one of the most important things that you take away from looking at this figure. Now, in the subsequent slides that we look at, right here, I've reorganized the amino acids and classified them into 2 major groups, polar and nonpolar. There are amino acids that are polar, in which case there's some electronegativity difference somewhere on the R group. And then there's amino acids that are nonpolar. The R group does not have an electronegativity difference or a significant electronegativity difference between any of the atoms on it. Now, one of the things that I want you to recognize and appreciate about this is that this classification of amino acids, proteinogenic amino acids, has basically nothing to do with the backbone. The reason for that is the backbone is involved in a protein structure. So we don't need to worry about the backbone. We basically ignore it and we only think about the R groups. Does that make sense? So whenever we go from here to here, we've gone from 20 randomly organized amino acids. I mean, heck, the names aren't even alphabetically organized. To now, okay, we've got nonpolar and polar. Okay, that's a little bit easier to digest. We've gone from, oh, I've got to learn 20 structures to I'm going to learn 9 structures for my nonpolar amino acids. And then separately, I'm going to learn the remaining 11 structures for my polar amino acids. Then we can break those groups down a little bit. My nonpolar amino acids, well, I see 2 of those nonpolar amino acids that have rings. Those are my aromatic amino acids. Then for my polar amino acids, I've got, well, amino acids that I'm going to classify as positive and those that I'm going to classify as negative. Now, what's important to recognize about these different classifications is that this definition of negative or positive, that is based on a neutral pH. So a pH of 7. So if I say glutamic acid is, and I'm going to switch colors here because that red doesn't show up so well on red. White will show up well. Neutral pH. If I say, oh, glutamic acid is a negative amino acid, and you look at this structure right here, your eyes will not deceive you. You're going to look at that and you're going to be like, I don't know where the heck the negative is. Is it like a moody amino acid or something like that? It's going to listen to the Smiths later today. No. Instead, this is an amino acid that is negatively charged because at a neutral pH, so a pH of 7, this group right here is going to be deprotonated, so it's going to be negatively charged. This group right here is going to be negatively charged as well. So the form of the predominant form of this molecule will have an overall charge of -1. The R group specifically is negatively charged at a neutral pH. So these classifications come from that right there. So we've gone from, hey, you've got 20 proteinogenic amino acids that you have to learn to, well, there's actually kind of positive polar, negative polar, polar uncharged, aromatic nonpolar, and nonpolar. You've got 5 different groups that you have to learn the structures of. So it's a little bit easier to digest. Now, the one group that I mentioned is your polar uncharged. No, I didn't spell that right. Unharged. Go with charged. Your uncharged amino acids. That means that these R groups, cysteine, tyrosine, glutamine, threonine, asparagine, serine, basically at any and every pH, those R groups are going to have no charge whatsoever. So what that means is glutamine. People like to see this group right here, this nitrogen, and they like to say, oh, that's NH2 with a lone pair of electrons. And I know when I see a lone pair of electrons, I can throw a hydrogen on there. At a pH of 1, surely it's going to be positively charged. No. Do not fall for that trap. Do not fall into that. The reason that it will not is because what is right next to that nitrogen? A carbonyl carbon. That carbonyl carbon is basically going to make this group completely unattractive to a proton. So this group will not adopt or pick up a proton. So when you're looking at your amino acid structures, don't look at this. Look at something like this. Break the groups down so that's easier to process. I think I accidentally raised my own hand. Or is there a hand that's been raised? I raised my own hand. Okay, so I'm going to go ahead and I don't even know how I did that. I must have hit my keyboard. Chat. Let's see, participants. I'm going to lower my hand. Can I do that? Oh, it just. Oh, does that do anything? Oh, well, I guess my hand will be up. I'll be the ignored student. Okay, so that's okay. Anyway, so process it like that. Now, to break these groups down a little bit, we have polar charged, polar uncharged, I appreciate it, Christian. I'm gonna ride it out. Now it's gonna be a thing. Maybe I'll raise my hand every class. And maybe there's someone who's not paying attention at the moment and they're going to join in and they're gonna be like, why is he raising his own hand? I don't like this. Okay, so our negative amino acids, aspartic acid and glutamic acid. Our positively charged residues are lysine, histidine, and arginine. Personally, the way that if I could go back and relearn my amino acids in any form or fashion or any way, I would start with my negative residues and then go on to my positively charged residues. In part because the negative polar residues, there's only 2 of them. So that's like the smallest group you can possibly get at. In addition to that, their nomenclature. They are both acids. So you kind of have that as a little bit of an advantage of you can say, okay, my acidic residues. Oh, whenever I hear acid, my mind immediately is triggered to say, okay, negative residues. I'll use those terms interchangeably. Positive residues, lysine, histidine, and arginine. Those are all going to be positively charged at a neutral pH. Now I'm going from my group of 2 to a group of 3. And if I look back at this overall structure, in terms of groups or amino acids that are ionizable, those are my 5 most interesting amino acids. These are the ones that are most likely to participate in any sort of ionic interaction between R groups in a protein. So those are your structures. Now, did I highlight and say every single one of them? Yes, but I did it in kind of a quick fashion. What I would recommend doing is if I were to triage it, I would say first, second, third. Then I have my polar residues. I've got my polar residues down. There's a total of 11 of them. And I've looked at the positive and the negatively charged residues. Then I'm going to go on for my aromatic residues. And then last but not least, my nonpolar residues. Do I put those nonpolar residues that are not aromatic last because they're boring? Yes. Okay, so those are our structures. I want you to be able to identify those. Obviously, you're not going to need to be able to draw them, but I want you to identify those residues. Now, in terms of knowing their names, well, I've given you the full names. I expect you to know the full names. In 1966, there was a paper published that was IUPAC IUB Commission on Biochemical Nomenclature, Abbreviated Designation of Amino Acid Derivatives and Peptides, the Tentative Rules. So this is a paper that's basically like, hey, good news, guys, we came up with some rules. And those rules are something that they might feel like a little bit of a burden, where we take these 20 amino acids, these 20 proteinogenic amino acids, and we come up with 3-letter codes for them. Aspartic acid is SRE. Isoleucine is ILE. Lysine is LYS. Glycine is GLY. Okay, well, good. A handful of these, it's the first 3 letters of those amino acids. And that's all there is to it. But then other ones that doesn't really align. Now, a couple of examples that I want to highlight, and I'm going to jump back to the structure in just a minute, is I want to highlight glutamine and glutamic acid. If you look at the first 3 letters of each of those words, glutamic acid and glutamine, they both start with GLU. If you gave them both GLU, there'd be no way to differentiate between the two. But what I love about this is if you learn the structures in the sequence that I recommended, then you know the structure glutamic acid. And maybe you haven't gotten to glutamine yet. Well, what do you think the difference between glutamic acid and glutamine is without looking at them? It's an N. It's a nitrogen. If we look at the structure of glutamine and we look at the structure of glutamic acid, I've got to do a little bit of erasing here. Here's glutamic acid. right here, it has a carboxylic acid on its R group, glutamine. If you look at this central carbon right here, this is your alpha carbon. The first carbon off of a carboxylic acid is your alpha carbon. They both have an alpha carbon. All of our proteinogenic amino acids have alpha carbons. Then they've got this beta carbon, a beta carbon. Then we've got a gamma carbon, gamma carbon. And then we've got this carbonyl carbon. Oh, there's a carbonyl carbon on glutamic acid, but it's a part of a carboxylic acid. Well, the difference between glutamic acid and glutamine is rather than an OH completing our carboxylic acid, instead we have an NH2. GLN, that N right there. So effectively, the difference in the synthesis of glutamic acid and glutamine, you can make glutamine from glutamic acid by aminating it, by adding an amine to it. And so we have this naming scheme that kind of, it gives you a little bit of a hint about the structure of it based on or it gives you a little bit of a hint about the R group based on this 3-letter code. So there's a rhyme or a reason to this. So aspartic acid. Aspartic acid is just like the structure for glutamic acid because it has a carboxylic acid. Well, the 3-letter code for aspartic acid is ASP. The amino acid that is similar in structure to that is asparagine. The first 3 letters for asparagine are also ASP. Well, we can't use the same ones, but asparagine is aminated aspartic acid. So there's a little bit of a method to the madness, and don't just look at them as, oh, well, this is arbitrarily decided. There's little tricks for almost all of your amino acids. One that stands out is isoleucine, ILE. That didn't get ISO. And if you've taken organic chemistry, which I hate to remind you, but you all took organic chemistry, how often do you see ISO in organic chemistry? More than once. You see it, I would argue, enough. So that if we were to use ISO here, it's a prefix that would be kind of redundant and confusing that it could cause problems. So they came up with ILE. Okay, so for most of your amino acids, they have a 3-letter code that corresponds to the first 3 letters, or they have something that gives you a little bit of insight into the structure of that amino acid. So those are your 3-letter codes. Next up is your 1-letter codes. And in 1968, there was a paper that was published that was IUPAC IUB Commission on Biochemical Nomenclature, a 1-letter notation for amino acid sequences, the tentative rules. So it's almost like, hey, those 3-letter codes, that was a hit. So let's see what 1-letter codes we can come up with. But really what we can do is we can credit this woman right here, Margaret Oakley Dayhoff. In the 50s and 60s, I believe she was a PhD student at Columbia University, and she was studying protein folding. And she was a bioinformaticist back in the 1950s, which blows my mind because I learned about the field of bioinformatics in like 2006, 2005. And that to me was just like, oh, wow. So you use computers to study proteins. Neat. And I remember thinking to myself, well, they must have just cooked this field up a couple of weeks ago because I'm just learning of it now. And I mean, computers, whew, they're the wave of the future, they say. Well, that's just a myopic and ignorant view of the world, which everyone has those at some point in their lives. But she was studying protein folding with those, long cards that you would feed into a computer at the time, and it would tell you, do some massive calculation. She was doing that in the 50s and 60s. And that's just like, yeah, it's mind-blowing to me. And what she came up with was, hey, whenever she's programming or when she's writing a program to do a calculation about the free energy of a protein, if you have 20 amino acids and you have to write out their full name, it becomes a very long and bulky program. So she is the person who is credited with appropriately coming up with, we've got to have some simpler identifiers. And so it's her work that led to taking full names of amino acids and distilling down and coming up with a single and 3-letter code to identify an amino acid. And so what I always like to do is like to say, okay, well, we know the 26 letters of the English alphabet. There are 20 proteinogenic amino acids. So by knowing the 26 letters of the English alphabet, you know all single letter codes of your 20 proteinogenic amino acids because you know the alphabet. Now, associating those might take a minute. But what I like to do is just make or give myself a list of the 26 letters in the English alphabet and say, okay, well, I can cross out 6 of these. And I'm at, let's see, B is out, O is out, Y is out, U is out. That's 1, 2, 3, 4, 5, 6. Okay, those are my 6 letters that are out. So really, there's my 20 single letter codes. Done. I got to associate them though and assign them. And that's what the assignment looks like. For many of these, it is the first letter of the amino acid name. There are some that do not align perfectly with that. And whenever it comes to, oh, well, how am I going to learn this? Well, you already know the 20 letters, so that gives you a step up. Next, it's a matter of coming up with a simple mnemonic. There's some people who come up with or mnemonics that I always like to fall back on are a pirate's favorite amino acid is R, arginine. R is your single letter code. Done. Glutamine. Well, I'll let you know which the cutest amino acid is. It's cutamine. And so when it comes to, oh, well, which are the odd ones? There's really not too many of them. So there's like 5 letters that you have to know unique codes for. The last one that I'm going to share with you, and then I'm going to come back to this, is tryptophan. The single letter code is W. If you look at the structure for tryptophan, which is right here, and you tilt it on its side, it makes a W. Does it take a little bit of mental gymnastics to come up with that W? Yeah, it does. Is it better than nothing? Yes, it is. Now, as we go back, I remember a few semesters ago, I had a student who was like, I don't like that. That's fine. You don't have to like it. The rhyme or reason, and if you want this paper, there's the title, Journal of Biological Chemistry. That paper details where these single letter codes and where these 3-letter codes came from. If you want and this was the part that the student objected to, was I said, it's basically the first letter of every single amino acid. As we scroll through these, well, aspartic acid doesn't fit, glutamic acid doesn't fit, lysine doesn't fit, tyrosine, tryptophan, arginine, glutamine, and asparagine. So we've got 1, 2, 3, 4, 5, 6, 7, 8 amino acids that we can't use the first letter of their amino acid. So then this committee said, well, what are we going to use? And this was the part that the student was upset with. They're like, well, where did it come from? And I said, if you look at the paper, what it says is they use phonics. They used the phonetic pronunciation of these words to come up with something. So whenever they said, or whenever someone says aspartic acid, that RT sounds almost like the letter D, aspartic acid. So that hard T, obviously they couldn't use T because T was being used by threonine, but they assigned aspartic acid the single letter D. Structurally, which amino acid is most similar to aspartic acid? Glutamic acid. They use the phonetic pronunciation of aspartic acid to assign the single letter code D. And then they said, okay, well, what is most similar to this? Well, glutamic acid. Glutamic acid does not have a single letter designation, so we're going to give it E, because E is the next letter in the alphabet after D that is not being used. Glutamine. Well, it is Q. Why? Because you can pronounce glutamine with a Q-tamine. And so that's an instance where the student expressed frustration, and I cannot appease that. It might sound silly, it might sound hokey, but that's absolutely how it was determined and how it was agreed upon. So that's where these are coming from. I think that it's great because, hey, that's a practical idea. That's a practical solution. And then some of them, it was just, well, we don't want to use this because it's already used for this. For example, when you think about the single letter O, whenever I think about the single letter O, and then I think of organic chemistry, I think of ortho versus para. So ortho, and then this molecule or this group is para. Well, that's why we didn't want to use O. P, yeah, you've got to use it. But if there's a way that you don't have to use something, let's not use it. So that's where this came from. Now, I personally like to think about these as not just 20 random letters, but instead there's a rhyme or reason to it. I think the better understanding you have of the structures and the names, they're going to feed into one another. They're going to kind of support one another. To me, whenever I was learning, like as an undergraduate for my biochemistry classes, I learned my amino acid structures for the exam, and then I just kind of limped through. Then when I got to graduate school, I was like, oh crap, I'm not going to be able to do that. My decent understanding of them is not going to be adequate. And for me, what was most helpful was to look at the groups. And then the day that I saw aspartic acid and glutamic acid and recognized, oh, well, aspartic acid and glutamic acid, I think about them as siblings. Aspartic acid is the shorter of the two siblings. We've got alpha carbon and then CH2 and then my functional group. Glutamic acid, alpha carbon, CH2, another CH2, and then functional group. When that clicked, I was like, oh, I can draw aspartic acid and glutamic acid in my sleep. Then it was also helpful to then think about, well, what are my codes for asparagine and glutamine? Well, they're the same thing. They are just with this NH2 on there. That's what I think is extremely powerful and extremely helpful. So some people will they'll take this and they'll cut it up into 20 pieces and they'll make flashcards. Great. I think that you're going to have a more precise and surgical approach and more effective approach whenever you break it down like this and make your flashcards based on that. And you ask questions like, which of these amino acids is a positively charged amino acid? Which is negatively charged and which is a polar uncharged residue? Because I'm going to ask those sorts of questions. Now, before I proceed from this slide, one of the things that I really want to stress to you is think about the terms polar and unpolar or non-polar. Whenever I think of polar, I think of water, something with a partial positive or a partial negative charge, something with a pole, a positive pole and a negative pole. When I think of something that is non-polar, I think of not having a positive or a negative pole. It's neutral electronically. I bring that up because whenever people are learning the different organizations, they'll say, okay, I've got polar, positive, polar, negative, and then polar, uncharged. And then my other groups, I've got nonpolar, positive, and then nonpolar, negative. And then they'll say nonpolar, uncharged. Okay. They run into the problem because they don't pause and think about this. If something is nonpolar, how on earth could it be positively charged? Because that would imply that it has a positive pole. Similarly, nonpolar negative, also unnecessary. So nonpolar positive and nonpolar negative are not categories. Nonpolar uncharged, that is basically a redundant term. Because if it's nonpolar, yeah, it's uncharged. So your groups are polar positive, polar negative, polar uncharged, nonpolar, and then you have that subgroup or that subclassification of aromatic or nonpolar aromatic. Is everyone good with all that? Okay, great. So Margaret Oakley Dayhoff, absolutely fantastic that she was a bioinformatician before bioinformatics as a field was kind of even acknowledged as a field. Okay, here's our different groups kind of laid out. Your diprotic amino acids, here they are as single letter codes. With your diprotic amino acids, all that you have to worry about is the N-termini and C-termini pKa's. Your triprotic amino acids, if you look at this, we've got glutamic and aspartic acid, histidine, lysine, arginine, and then we've got these last two, tyrosine and cysteine. Well, let's think about those functional groups, tyrosine and cysteine. Tyrosine, hydroxide group. Cysteine, a thiol group. So those two, at the right pH, can be deprotonated. At a neutral pH, those are going to be uncharged, though, because they fall into this space right here. Now, I bring this up because there are some amino acids that, or there are some textbooks and some sources that will highlight certain residues as being ionizable and then others as not being ionizable. What I want you to be kind of thoughtful of and aware of is the pKa chart that I give you. So if I give you a pKa chart of, let's see if I have it on here. Yeah, if I give you, so here's our diprotic amino acids. These are all of the amino acids that have two ionizable groups. Every single one of these amino acids drawn here will have a titration curve that looks basically like this. I didn't draw that particularly well, but I'm going to redraw it because that looks particularly crappy. There we go. That's better. So here's 0.5, 0 or 1.5, and then 1.0 and 2.0. Every single one of these amino acids will have a titration curve that looks like this. Nothing more exciting, nothing less exciting. Every single one of these amino acids will have a triprotic, or is a triprotic amino acid, and will have a titration curve that looks a little bit more interesting. We'll have 0.5, 1.5, 2.5. Now, if we jump back and forth between these titration curves, another way that you could describe this is a diprotic amino acid will have two horizontal regions or two buffering regions. A triprotic amino acid will have three horizontal regions or three buffering regions. Now, what's important whenever you see a titration curve and whenever you see pKa values is I think that it's helpful to basically be ready to ignore any labels and instead say, okay, I know roughly what the pKa of a carboxylic acid is. A pKa of a carboxylic acid is going to be acidic. So it's going to be about 2, maybe 3. And given these options, these 3 columns, 1, 2, and 3, these are going to correspond to specified groups. One, I've got this labeled as, or group 1 could be all of the C termini, the R group, or the N termini. Group 2 could be the C termini, N termini, or the R group. And group 3, or this third column, could be the C termini, N termini, or R group. Now, I'm going to give you the labels, but I just want you to anticipate if you were to see PK1, PK2, PK3, to be kind of dynamic in what you see and be thoughtful about what you see and not say, oh, well, I know, or I've seen this table so many times and the first one is always the carboxylic acid. Well, is a carboxylic acid going to have a pKa of 10.25? No, it's not. And if you don't know, like if you're taking the MCAT and you see a column like this, pKa1, and you see 10.25 and you're like, well, I've been trained to learn the first column is always the carboxylic acid, you're in trouble because then you're going to draw your molecule or you're going to identify the molecule incorrectly. Does that make sense? So I want you to, whenever you see this sort of chart, anticipate what it is and say, okay, well, all of the ones in column number 2, they range from 1.77 to as high as 2.20. That's probably my carboxylic acid. Now, 3, oh boy, these are all over the place. We've got as low as 3.86 and as high as 12.48. That's impossible for them to be, if they're as a 3.86 can't be an N termini, just as 12.48 can't be a C termini. So this has to be my R group, because my R groups for glutamic acid and arginine are radically different. So those are going to have radically different pKa's. Does that make sense? So my last group, well, these are all approximate, or these are all, I would call an average of about 9. These are all an average of about 2. These are all, oh man, they're all over the place. So what I'm telling you is really just to anticipate if you take the PCAT or the MCAT or some sort of standardized exam where you get a chart that doesn't identify, well, this pKa came from this functional group. This pKa comes from this functional group, because you might see them labeled as pKa1, pKa2, pKa3. I want you to read, it's almost like you read the room and you're like, okay, these are all similar. So they're all probably from this, or they're in a column together, so they're all from the same functional group, and that would be the C termini. Does that make sense? Okay, great. So a triprotic amino acid, or all triprotic amino acids, are going to have a titration curve like that, what is shown on the right-hand side. And that's going to give you 3 horizontal regions. Now, if we can look at an amino acid like lysine, lysine and arginine are 2 amino acids that people kind of struggle with, in part because when they draw lysine, they see a group like this and they start, and I'm speaking from my own experience where I drew my alpha carbon and then I think, okay, well, it's like a long line of carbons. CH, CH. And then my attention span goes south, and then I'm just like, how many CHs have I drawn and how many do I need to draw? And I've drawn a lysine that looks a little bit like this. I think it's like 6 of them, and then you get NH3 at the end. Oh boy, I hope that's right. I think that it's helpful, especially since y'all don't have to draw anything. I think that it's helpful for y'all to practice in a way like this. Here's my alpha carbon. CH2, 4, NH3, plus. Done. I saved myself the time, saved myself the stress of drawing all of these atoms, and I avoid that sort of mistake. Now, lysine has a single letter code of K. It has 3 ionizable groups. 1, 2, and 3. The way that I've drawn lysine here, well, this is at a very low pH. What is the charge of lysine as I display it right here? +2, because all of my groups are protonated. Now, lysine with all of my groups protonated, I'm going to go ahead and put together my 3 dots. Now, this one is 2.18. That's my first pKa value. My next one happens to be my amino group, 8.95. And my third ionizable group is my R group. That has a pKa of 10.53. I haven't really drawn this to scale very well, but I'm not going to lose any sleep over that because I just want to show an example. There's my 3 horizontal regions. I think that it's helpful to think about which group is going to be deprotonated first. Well, if I've drawn it at its most acidic form, I'm going to add sodium hydroxide to it. The first group that's going to lose a proton is this one. Why? Because it has the lowest pKa value. My next group that's going to lose a proton is this one right here. Why? Because it has the next lowest pKa. And then the third and final group that's going to be deprotonated is this one right here. Why? Because it has the third highest pKa value. Don't fall into the trap of thinking, well, you deprotonate the C termini, then the N termini, then the R group. Does not matter. What matters is, what are the pKa values? You go from lowest to highest. So if we look at lysine, it's CNR. If we look at arginine, it's CNR. If we look at glutamic acid, CRN. So that's one of the places where people will kind of fall into a trap because they'll think, oh, well, this is the pattern. It's not the pattern. It's the pattern of lowest to highest. That's all there is to it. Now, when we look at an amino acid like lysine, one of the things that I always like to do is I like to line up the charges or line up my pKa values. I'm going to list them from lowest to highest. 2.18, then 8.95, then 10.53. And what I'm going to do is I'm going to say, all right, well, if my pH is below 2.18, the predominant form of my molecule will have a charge of +2. Now, when my pH is above 2.18, then this group right here is going to be deprotonated. So I'm going to lose this proton, so this group is going to be negatively charged when my pH is above 2.18. So that means my molecule is going to have a +1 charge. When my pH continues going up, so when it's greater than 2.18, all the way until it hits 8.95 and then goes above 8.95. When my pH is above 8.95, now I'm deprotonating this group right here. My charge, well, that group's going to be deprotonated. So that's going to not be positive, but instead it's going to be neutral. My charge of my molecule is going to be 0 because this negative offsets this positive right here. When finally my third group gets deprotonated, my molecule will have a charge of -1. Does everyone follow that?
I have a
Okay.
question.
Yes, go.
So when the pH is it from 0 to 2.18, then it's a +2?
That's a great question. The predominant form is +2. Now,
Okay.
there's a little nuance to it because as you get closer to 2.18, there's a little bit of that +1 in there. Because when pH equals 2.18, we've got 50% that's +2 and 50% that's +1. And that doesn't just go from it's 100% plus +2, and then all of a sudden it's 50%. Instead, it's very gradually increasing to be 50-50.
Okay.
Does that make sense?
Yes.
Okay, great. So let me erase that real quick. So
Do the same with any other amino acid. So if you picked the top one, so it would be 2.05, then 8, then 10. And then it would just be those exactly how you, so +2 first, then between the next two values, it's +1, and then it's 0, and then -1.
it's close to that. This is
Across
where,
that spectrum.
yes,
Okay.
it's not necessarily going to be +2 all the way to -1. Some of them are +1 all the way to -2. And that's going to vary with amino acid to amino acid.
Okay. Okay. And then did you already go over how you determine that?
Well, that's a great question because if we remember, lysine is a positively charged residue. So lysine displayed here has an R group that's positively charged. So it's going to
And
have two positive charges.
and yeah, starts at a positive charge.
Yes. So
Gotcha.
think
Okay.
that's why if we go back, or anytime you look at an amino acid, that's why I like to start out with, here is my extreme where it's fully protonated. It
Right.
is +1. Great questions.
Okay. Cool.
So if we are gradually increasing our pH and we're seeing this kind of range, this spectrum where a molecule goes from, oh, the most common form is +2, then it's +1, then it's 0, then it's -1, then we get to a point where we can say, all right, well, at what pH is my molecule going to be, 100% 0?
And that's when you take the two and you divide them by,
Yes,
you add them together and then divide them. Okay, cool.
perfect. So this is this point where my molecule is 100% 0. That is a very special and unique point. This is known as my isoelectric point, or my PI, isoelectric point. So this is where my molecule has no net charge. And I say that no net charge because what some people have a habit of doing is they say, oh, well, that's where the molecule is uncharged. And it's like, well, overall, but does it have charges? Yes, it has charges, but some of those charges cancel one another out. So my PI, my isoelectric point, is where my molecule, 100% of my molecule has no overall charge. The positives cancel out the negatives. And the neutral groups, well, they don't cancel anything out because they're neutral. Now, This is also a significant point because this is where your molecule is least soluble. Now, if you think back to Gen Chem 2, you had precipitates, and those were insoluble substances, salts that basically fell to the bottom of the beaker because they wouldn't go into solution well. Proteins do the same thing. And lots of people have examples of this if they take like, or if they ingest, if they eat whey protein. Like if you go to the grocery store and you get whey protein and you add it to water, you know, all the advertisements are like, oh, this just goes into solution very well. Well, if you've ever done that, you realize you add the powdered protein and it like doesn't go into solution well because water is a polar substance. And spoiler alert, there's lots of amino acids that are on proteins or in proteins that are non-polar, that don't like going into solution. And so can you combat that? Yes, you can. You can combat that by adjusting the pH, by getting certain groups to be protonated and kind of repel other positively charged groups or something like that. But here what we have is a PI calculation where you have the two pKa's that are on either side of your overall charge of 0. Now, I specifically go after a calculation of a triprotic amino acid because when you see something like, to calculate the PI for a diprotic amino acid, you take the two pKa values and you divide by 2, and you're done. Here, how many pKa values do you have? 3. Do you need all of them? No, you do not. You only need 2 of them. And that's where people run into problems because I will give you questions asking you to calculate the PI of histidine. And there will be someone who will say 9.18 plus 1.77 plus 6.10 divided by 2, divided by 3. And they'll just kind of cross their fingers on that. Here, what you need to do is you just take the 2 that are on either side of that charge of 0. And you get, well, that divided by 2. And that is your PI.
So to determine that, that's whenever it depends on which amino acid you choose, because that determines like where you'll start, whether it's a +2 or a negative or a -1 or whatever it is.
Yes. And so
Okay.
the next slide, we're going to do an example of that. So this is aspartic acid. Aspartic acid, single letter code of D. I'm going to toggle back and forth between these slides. The C termini is 2.10. So 2.10. That's my pKa for that. My N termini is 9.82. 9.82. And then my R group is 3.86. 3.86. So we've got these 3 groups. We have a molecule that, what's our overall charge as it's displayed right here? We've got a positive, nothing, nothing. So would everyone agree that it's +1?
Yes.
Okay. Then when we go from +1, well, when we deprotonate our group with the lowest pKa value, this one right here, that's going to give us a -1. So that means that -1 and +1, those cancel out. So we get a molecule with an overall charge of 0. The next group we deprotonate is this one right here with the next lowest pKa value, 3.86. And when that's negatively charged, we've got 2 negatives and 1 positive. That's going to give us a -1. And then my last group, my N termini, when I deprotonate that, that's not going to be negative. It's just going to be neutral. And so that means I've got 2 negative charges and 1 0. So that's going to give me a -2. So that's my range of possible charges. This is a question that I always love to ask where I say, well, can aspartic acid have a -3 charge? It can't. Can it have a +2 charge? It also can't. every amino acid has a range of charges that it can adopt. So from +2 or +1 all the way up to -2, it's going to vary a little bit. What you need to be able to do is kind of recognize patterns and recognize what individual amino acids do. Now, a little bit of a spoiler, do you think that glutamic acid, based on this right here, is going to kind of follow the same pattern? It will, because glutamic acid and aspartic acid are almost identical in structure, and they're both your negatively charged residues. Now, what we're going to write are our pKa values in increasing order: 2.10, 3.86, last but not least, 9.82. If I want to calculate my PI, I've got 3 pKa values. I don't need all 3 of them. I just need 2.10 plus 3.86 divided by 2, and that gives me 596 divided by 2, 2.98, I think. So when the pH equals 2.98, 100% of my molecule is going to have an overall charge of 0. Now, what does that correspond to what my molecule looks like? Well, it's going to look like this. When 100% of my molecule, or sorry, when my pH is exactly 2.98, 100% of my molecule looks like what you see on the right-hand side. The N termini is protonated, the C termini is deprotonated, the R group remains protonated. So that's what we just did, calculating the isoelectric point. This is also a triprotic acid, so it's going to have a titration curve with a total of 3 horizontal regions. And that got worse as I continued drawing it. But it is 3:40, so I'm going to go ahead and stop right here. Tomorrow's lecture will be asynchronous, so I will finish this one up, and then I'll add some more content to the remainder of that. Friday, we'll meet at our regularly scheduled time on Zoom. I'll be available to answer questions. But other than that, we'll just go through a regular sequence. I am going to be posting a quiz tomorrow. That will be, so you'll have actually 2 quizzes this week. Tomorrow. And I want to make sure that everyone does it because we're going to do it with Proctorio. And I just want to make sure that that works for everyone so that we don't have any technical issues running into Monday. So I will add that. There will be some top hats added today to reflect our previous work, and yesterday as well as today. And what I'm going to do for top hat is just have them all due on Monday at 12 p.m. whenever our exam starts. You'll have the chance to ask questions prior to then, but I will post those before the end of the evening tonight. I'm going to stop my recording.